Adam. Okay, good. I can't get rid of this this thing here. Just let me hide floating meeting. That's it. Okay, thank you, Kiralee, and thank you everybody for watching this presentation. I'm actually very happy that ANBUG has come to us and asked us, could we do, that's the entire group, the inelastic scattering group, can we do a lecture series based around inelastic scattering? That is something that I wanted to do for a long time, actually, before I was even the group manager. And I'm really happy that we are sort of on our way to doing that. And I would like, this would be a sort of a segue into more intense workshops that other groups are holding, practically yearly. I think the diffraction group is, and the small angle scattering group is. And I really hope that these lectures are of interest to you. Certainly I'm very interested in them, and I'm glad that they're being recorded. And again, I thank you so much to the organizing committee and to the committee of ANBUG giving us the opportunity, which is a really nice opportunity for us to start doing these type of series. So I do speak a lot, so I'm going to have to always watch the time too. I can speak on and on and on. And I've told Kiralee, she asked me how long will I speak for, and I said hours, but I'll try and keep it to about 40 minutes. So today I'm going to be speaking about the what I would call energy filter type neutron spectrometers. There are a few in the world. The one that we built here at ANSTO is one based on the NIST design. It's practically a copy of the NIST design. I think it's probably a little bit better than the NIST design in a couple of ways, not a huge number of ways, but a little bit better. And so that's what this talk is based around, this type of spectroscopy. I did say in the abstract that I would touch on backscattering spectroscopy. That's not really my bag, and in fact, really, we should have an instrument scientist who is doing that work, give you a presentation, and it's very interesting work, and I'm sure they'll be able to do it. They're being tied up, but in about a month's time, hopefully, we'll have a lecture about that. I will touch on it very briefly, but it's only very briefly. Okay, let's get into it now. So we're going to go on a journey of neutron spectroscopy using the Briggs filter. And now I'm going to review physics, the physics involved with energy filtered spectroscopy. I'm sorry if I might be going over things that Kiralee and Richard and sorry, not Richard, Dae-Hong and Shin has already covered, but I feel like it's very important to sort of get our minds into it and understand what we're actually measuring. It's very important. Then I'm going to give some case studies. I'm going to do it the other way around. So it's not the how the Briggs filter works. It's first the case studies and then how the Briggs filter works. So you have to be patient with me. So inelastic neutron scattering covers a huge, absolutely enormous range of energies. 5 decades of energies from, and so this is a very funny scale. It's a log 10 scale. You've got to get your brains into it a bit, got to get your brains into it. So 0 means 1 wave number. So this is wave numbers here. And so 1 means 10, 2 means 100, etc. Another way of looking at it is that this 0 means 0.1 millieV. This 1 means 1 millieV. 2 means 10 millieV. Sorry, and maybe I've got it a bit wrong. And then 5 means 10 EV. 10 EV. So you're going from micro EV right up to 10 EV. So it's a huge spectrum. Okay. We cover this range here at ACNS. In particular, the quasi-elastic scattering, Pelican reaches that range, and also the backscattering reaches that range. It's in the micro EV range for the EMU instrument. Here we're going to be talking about what we can do with lattice modes and intramolecular modes, basically vibrational modes. And that's what we're measuring. And it's very, 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 very similar to infrared and Raman spectroscopy. Extremely similar. The biggest difference is, of course, we're using neutrons. It's not light. And the other difference is that we're looking at the entire Brillouin zone, not just the gamma point. So the gamma point, because photons don't have any momentum, right? It can't, you know, the only scatter they are looking at is the gamma point, whereas we're looking at the entire Brillouin zone because we've got momentum. Okay. Oh, and then the other thing is this SQ of omega. Sorry, I flipped. That's an important thing. So this Y axis is what we call SQ of omega. SQ of omega is a scattering function. It's an interaction function. It's when the neutron comes in, interacts with the material, and scatters out. Okay, that's what SQ of omega is. SQ of omega can be directly related to, in the case of neutrons, to phonon density of states, in our case, the phonon density of states, and the molecular vibrations within the molecule itself, which is very similar to what you would see in an infrared spectrum. Okay, so this is not what we get from the Brillouin filter. This is actually probably what you would get from the time of flight, but I'm just putting it out there so you can show. So SQ of omega relates to the Q space. In this case, it's along the y-axis, x-axis here, and omega relates to the transfer energy. So that's the transfer momentum and transfer energy. Okay, transfer energy here and transfer momentum. And you can see these peaks, and these where it's high in intensity, it means there's peaks there. So that corresponds to the elastic peak, and then there's some other types of excitation that one can relate to potentially a molecule that you're looking at. And this, when I talk about a molecule, I'm talking about solid state. I'm talking about something that's solid, right? And it's not gas. Okay. So that's what we can see. We can see bands, all right, that come up when we take our measurement. We see these energies. The other thing I'd like to note is the distribution of energy in Q space here. The distribution in Q space. In fact, it goes up and it goes down. It's like a normal distribution curve. And you can see that here. So that one of the general forms of SQ of omega, the scattering function, that what we measure along Q has this type of shape. It has a distribution, okay? It has a type of normal distribution, and that corresponds to two parts, and which I'm going to get to it, two parts of the scattering function. One part is in fact due to the Debye-Waller term, and another part is called the prefactor term. And that creates this distribution in Q. So we always see that. Along omega, which is the transfer energy, we're seeing how we would call it resonances occurring, because the energy that we're probing, the energy that we have of the neutron energy, the thermal energy, or the cold energies, or the higher energies, probe different states within the material. And they're probing the vibrations in the material. And those vibrations, they resonate with the neutron coming in, and we see that in our spectrum, in the SQ of omega. So in particular, in the range that we're looking at with the Brillouin filter, which is around about 10 millieV, right up to about 200 millieV, we're probing phonons and we're probing we're probing vibrations. And these vibrations in Q space are more or less constant, right? Except for this normal distribution that I was talking about, because of the Debye-Waller factor and this prefactor. There's a normal distribution, but they're flat. We probe the intramolecular vibrations, a bit like the like infrared and Raman, except over the entire Brillouin zone. Now, in the case of QENS, quasi-elastic neutron scattering, this is really looking at diffusion effects. So there, in the case of, I'm going to read this because I'm going to have a cheat sheet here. In the case of EMU, it has micro EV resolution. In the case of Pelican, I believe, and Richard Moll is here, so he can correct me, 50 to 350 micro EV resolution. It means that in terms of the time scales that one's looking at the dynamic region, the dynamic range. So the dynamic range of Pelican is around 2 millieV, I believe, and the dynamic range of EMU is around 31 or 30 micro EV. The 30 micro EV means that they're in the nanosecond regime. Okay, the nanosecond regime, whereas I believe Pelican's in the microsecond. Hopefully I've got that right. And then we've got up here, which we don't probe, unfortunately. We might get there. So we're thinking about maybe at one stage putting in a hot source into. So we have a cold source in the reactor, and we're going to replace that cold source with a new cold source next year. So there's going to be a shutdown between March 18 to July 4 of next year. We know we won't do any neutron work, so that's something if you've got to remind yourselves of. But we can also put in a hot source, and it could be, I think it might be tungsten or something, which then increases the energy range, the instant energies that can be delivered to an instrument. And we can go to about, I would say, reasonably about 500 millieV. It is possible maybe to go to 1 millieV, but normally this type of work, which is neutron Compton scattering or deep inelastic neutron scattering, this is mainly done, I believe, at spallation neutron sources, because they have these hot neutrons anyway. They get them for free, and they're normally trying to reduce the energies of them rather than have these higher energies. Okay. Now, there's two more slides to go with the physics of it. Okay, it may be boring, but it's very, very, very important. So the neutron scattering problem, and one needs to understand this it's very important to understand this in terms of the nuclear potential. When you think about neutrons, they're coming in, they're being scattered by the strong nuclear force, right? However, they're not exactly being scattered by the strong nuclear force. So a atomic nucleus, a nucleon, is about 10 femtometers. But, and the electron cloud is around 1 angstrom, which is 100,000 femtometers. So it's much bigger. In our case, we're having wavelengths of around 1 or 2 angstrom, right? That makes this problem, scattering problem, different. It's different. We don't have such a small wavelength. We have such a tiny wavelength. We have a large wavelength in comparison to the size of the nucleus and the nuclear potential, which is in the mega EV, the mega EV. Now, if you're trying to understand the scattering, you must then come to understand that you have to use the Schrödinger equation to describe the scattering, all right? So once you start doing that, then you have to use the Schrödinger equation to describe the probabilities. Then you have to use a wave function. Then the wave function can be like electrons, can be S-like, P-like, D-like, etc. Okay, but if you've got a wavelength that is so large, and you do an integration of all these wave functions, what you find is the only wave function that doesn't cancel themselves out at such large areas, large distances, is the S wave. The S wave. It has some parts of it are still appreciable. Everything else cancels out. And because of that, we're not looking at the potential here, we're looking at over here somewhere. So we start off with a wave function that is plane wave-like, okay? That's the instant wave. It has to be plane wave. It has to be. Really, that's the only thing it can be anyway. But the Hamiltonian, and I've used the Hamiltonian here in a sort of a classical way, classical mechanics, just to say, this is a momentum here, etc., right? But you don't have a normal, you don't have the nuclear potential, you have a pseudo potential here, that's C here, that gets the correct beads, which is just the scattering lengths. Because the scattering isn't negative. mainly. It's mainly positive. It's repulsive as opposed to attractive. Whereas this force here, the nuclear force, is attractive. Okay, so one needs to think about it in those terms, and we can't describe it completely, but we come up with this scattering equation here. So you have the Xi here, or Z here. Excuse me, I've got to remember the Greek way of pronouncing it. I think it's Z here, which is the hard sphere scattering potential. And then you've got the resonance terms. And this is the resonance terms is what we see. The resonance terms is what we see here. Okay. And so these are, this is the resonance for readmission. This is what's it called? The lifetime, full width half, the lifetime of the actual resonance itself, of the neutron. So there's a resonance of scattering resonance. And then there's also a absorption resonance here that comes into it. And so this is the incident energy, and this is the resonant energy. And it's the resonant energies that we see in our SQ of omegas that we measure. Okay. And so now you can go from here to here. So that's the Bright-Wigner equation. And now you can use Fermi-Golden rule to derive what we call the SQ of omega. There's a Y here. This is just a factor. I don't go into the factor. It includes Bose factors and all sorts of stuff, which is irrelevant. The Bose factor basically is just a distribution. Anyway, it's a normal distribution. It's irrelevant. It's relevant, but it's not relevant for us at the moment. The sigma is the scattering cross-section. It's a total scattering cross-section. So, for example, hydrogen has a huge scattering cross-section. So we do look at hydrogen a lot. Then there are these two terms here, right? And these two terms correspond to this relationship here. There's the prefactor term here, the Q dot U, and I'll tell you what U is shortly, which is this line here, and the Q dot, the exponential, which is the what is it? I've got my cheat notes here again. Oh, my brain sometimes the Bywaller, sorry, it's the Bywaller term here. Sorry, just sometimes I lose my thought. Okay, and this U is the atomic translation of the vibration. So it's how far the atom is vibrating inside the material. Okay, so it's Q dot R or Q dot U in this case. Okay, and there are two delta functions. Sometimes this equation is written in slightly different ways, and sometimes they drop off the deltas, but these deltas are important. Mainly, you'll see a peak when the transfer energy, which is the omega, is equivalent to the vibrational mode. Okay, when it's equivalent, then you'll see a delta function, and you get a peak. Okay. Also, equivalently within the Brillouin zone. Now we're doing a sort of angle integrated thing, so we all the Q's get integrated up anyway, so it doesn't matter in this case. But in general, if you were looking, say, at a triple axis experiment, then you also have to include Q, right? So Q will go to a particular part in the Brillouin zone, and when there's a transition at that particular Q, that momentum vector here, the transfer vector, is equivalent to the Q within the actual material itself, plus or minus a G vector, which is an umklapp vector. Then there's a transition. Okay. So we're going to do some case studies. I'm going to go through this. We've stopped the discussion of the physics, and now we're going to do some case studies. So a case study here is with octane. This is what we've done on the Brillouin filter. And immediately you see all these modes here. So it's very much like, I think it's better than, in fact, I'm not comparing it to infrared or Raman, but we see all the biggest peaks are due to vibrational modes of hydrogen within the octane itself. And this big peak here is due to the methyl groups at the ends of the octane here. So octane is C8H18. And what's interesting with octane is it's triclinic, and it goes to an orthorhombic, as an orthorhombic phase transition at some point here, which is interesting to look at. And there's the melting points around 216 Kelvin. And what's interesting is, that you can track the A, B, and C lattice parameters and alpha, beta, gamma. But this is with actually neutrons as well. But they deuterate the hydrogens to get this out. But what's interesting, we can just leave the hydrogens on and track what's going on with, say, the methyl groups, right? The torsional modes and the methyl groups, and we can track it. We can track the intensity as a function of temperature going downwards here. So here we've got SQ of omega. So this is the SQ of omega I've been talking about. It is on a slope, a background. I haven't taken the background out, and it's still a work in progress. I'm very slow with these sort of things because I'm fairly careful with these sort of studies anyway. But so there is a background. Most of the background is due to the elastic tail. In this case, it's the elastic tail. There is a sort of a hull structure here too, which is also due to the filter, but we're not going to go into the real nitty-gritty details of all of it. And this is still around. Well, this is interesting too, because this green is just above the melting point. So it's a liquid. We're still seeing peaks here. Now, those peaks might be due, and I think are due to the modes of the material, but we're still able to see it. What we see with neutrons is we see all the motion. So when we go to a liquid, in general, we should just see the background, right? Because we also see rotations and translations. And that's what infrared doesn't see, but we see that, right? We see everything. So that's why we have to cool. We have to cool the material down, so we get rid of all the bad bits, and we only get the goodness coming out. Okay, so that's a temperature study, but that's ongoing for me. As I said, I'm very slow with that. But we've got an example that's being published just fairly recently in 2022. By a person that was with us on actually the on the backscattering line in the scale Isles, and Will Gates, who's from, and it's not Bill Gates, but it's Will Gates from Victoria, from I forget the university in Victoria, and they did a study on the Brilliant filter, but then they went to, I think they may have gone to Pelican, but I think they also went to EMU and did they went to EMU and Pelican, I think, and did a study there as well, which is interesting. So that in this reference here, if you're interested in this type of work, you can look up the reference. I think it's reference 21, because I was looking at just a few days ago, and I still remember the number. So what's the interesting part of this is it's confined, it's water confined within montmorillonite, which is just clay. It's a mineral clay. Okay, and this is the structure of the mineral clay. But what's interesting about clay is it can absorb huge amounts of water, just as more than its weight, in fact. And that's interesting in industrial and environmental applications, apparently. And so what's interesting is really to really tease out what is the structure, what's going on with the water within the clay. Now, in this case, we have to freeze it, okay, because we've still got to look at it at low temperatures. I'm a little bit dubious about that. Maybe we could, in fact, look at it at more room temperature, but I'm not sure whether they did that. But anyway, that's okay. And this is quite an intricate study where they're looking at different types of frozen water. So water goes into lots and lots of different phases, huge number of phases, and it's still an ongoing study, in fact, worldwide of the different phases of water. We've taken those phases of water and compared them. We've done an identification study of the spectra. So we know what the spectra of clay looks like, and we can subtract it out. And then we can subtract out, say, 24% weight, gravimetric weight of WC. I'm not sure what the C stands for now. I've forgotten the clay. And see what it looks like, etc. So what they found is that there are two types of forms of ice observed in the larger pores. So they make pores inside the clay. The hexagonal and cubic, and these have specific, it's a bit like infrared, they have a specific structure, a specific type, you'll see that shortly. And then there's also some interfacial ice observed. And I think it's actually a rather nice study. So these are this is the actual spectra, the spectra. So you've got oven dried here, which is basically, not much at all. And then you're putting in water progressively, and they compare it to a type of filter spectrometer that's at ISIS. It's called Tosca, and that's been around for quite some time. And so it pumps out a lot of good work. And then they've done a whole bunch of background subtracting different spectra from other spectra, and they get this type of results. And then they compare it to what is known. And so what is known is that there is in terms of the phonon structure, because we're looking at phonons now, they correspond to different high density of states within the Brillouin zone, and that corresponds to certain types of modes that they can relate to at a molecular level. And in that way, they come to these sort of conclusions. So actually, it's a really nice study. It's very difficult for me to summarize such a study in a few minutes. It would take at least half an hour to do properly. So I'm absolutely sure that I'm not doing a good justice to this work, because it is very nice work. But that's the type of thing we can do. So one of the other types of studies we can do with a filter spectrometer, or any sort of gas field. No, I'd say gas field. It may not be. It may be like methane or something within a cage structure, but it could also be a liquid actually too. In moths, clathrates, zeolites, etc. Organic materials. It's a no-brainer because it has a humongous signal. There's the total scattering cross section of hydrogen is 82 barn, and whereas deuterium is about 7 barn. So that's, there's just enormous differences, and we love hydrogen. For catalytic processes, which we haven't really done, we have the equipment to do it, but I would love to go further into that. It takes a lot of work, I know that, and one needs to have the right user groups to come along. They need to know what they're doing. That's for sure, with the catalysis part, because they bring the sample preparation essentially to us. And of course, then there's the vibrational densive states, and this is with, for example, with alloys or other materials, and that's interesting too. You might hear that with filter spectroscopy, brilliant filter spectroscopy, you only do incoherent scattering studies. No. We are measuring the total scattering cross section, and it doesn't matter whether it's incoherent or coherent. We see it, and I will show you an example right at the end on nickel on our calibration sample. Okay, so how does the Brilliant filter actually work? Well, if you haven't seen the Brilliant filter, this is it. It looks a bit like the TARDIS. It's this is in situ. This is in the Taipan area here, right next to the reactor. So we have a very small, what you call maybe like a very small conduit. It's sort of like a guide into the monochromator drum, and from there onto the sample, and then scatters from the sample into the spectrometer, into the analyzer itself. Now you may see that there's, if you note Taipan, we also have a triple axis, and what we do is we actually crane in this bit here, the TARDIS, right, with its trolley. We crane it in, and we disconnect the triple axis, and we put it to the side. So it is a big task, and it takes we give about a week, a few days to do it, 3 or 4 days to do this, to take it off, to take the triple axis off, and to crane in the Brilliant filter and to get it going. Now you'll see this is a compressor here, and we have 2 humongous cryo heads that cools all our filter blocks within the spectrometer itself, the analyzer itself, to below 80 Kelvin, to below liquid nitrogen, 77 Kelvin, to below liquid nitrogen temperatures. And I'll tell you why we need to do that. But because we have to cool all the blocks to that, everything has to be under vacuum. And there's this thing, the TARDIS, what you see at the moment is just the high density polyethylene shielding, but within that there's a stainless steel chamber, okay, and it's being pumped with a turbo pump and a roughing pump down to about 10 to the minus 7, 10 to the minus 8 millibar. Okay, so it's a big thing, and what this thing does is it moves around the drum. So as you change the energy, it goes to a different position. So it over in this point here, the straight through position, that's that's at the low takeoff angles, which means high energies. Say, for example, if we're on the PG, the pyrolytic graphite monochromator, it's at 70 millieV, and then we have to go all the way around to the other side, and we get down to about 5.5 millieV if we're lucky, because of course space is a limitation. You can see it all over here too. We have a cryostat here. So we actually have to, we always have a top loading cryostat. So we take out the stick from the top loading cryostat and put the sample on. The sample is a polycrystalline sample, so it's a powder sample. We've never tried a single crystal sample. It might be interesting to do that. And it's loaded into an annular can or a flat plate, okay? And there's the compressors and the pump. The roughing pump is out there, and the actual turbo pump sitting on top over here. And this thing is moving around the drum, and the actual compressor is outside the photograph, but it's for the compressor for the cryostat itself is over on the right hand side here, and it's well and truly out of the way. But as this thing's moving around, so it's moving around on air pads or air skates, excuse me, it's about 30 micron, 40 micron off the floor, and it moves around very slowly as we change the energy. Of course, when it gets to about 5 millieV, we have to watch how we position the cryo pumps. Okay, so what's a typical experiment? Typical experiment is you've got the reactor over here. Neutrons come through to the drum over here. They pass by a virtual, what we call a virtual source. It's a slit that moves in and out. We have it at the moment set at about 20 millimeters, 10 by 10. 10 minus 10, 10. And then we have the secondary shutter here. We don't have to worry about that for the moment. Obviously, it's open. We have some sapphire crystals, which reduce the background. We don't have to worry about that either. And it goes to the monochromator. We have two monochromators, as I said. We have one monochromator, which is a PG, which goes from about 5 millieV to about 70 millieV, and the other one, the copper monochromator, will go around about 15 millieV to 200 millieV, and that's a higher resolution monochromator. And then what it does is then it passes through, there are some collimators here, and there's a collimator here as well that we can put in, and the beam passes into the monochromated beam, passes onto the sample, and the sample scatters. Okay, now excuse me, we have 30 helium-3 detectors, position-sensitive detectors that are 40 millimeters long, so it's fairly long, and 2.5 inches in diameter. Okay, and they're filled to a pressure of 2 bar, which is not as much as, say, what we would normally fill, which is around, whether it's 13 or 12 bar or 10 bar helium-3. Why? Is because we want to be sensitive to cold neutrons only, cold neutrons. We're not really concerned about any thermals. In fact, we don't want thermals. They're considered to be background for us. And so the beam passes through, and this is the vacuum chamber here. Right, the vacuum chamber the detectors are outside the vacuum chamber, but the vacuum chamber is in this part here, and that's the vacuum chamber here. It's about 1 meter in diameter from sample to detectors, around about 1 meter. Just the solid angle that we take. So this is about 80 degrees solid angle, 80 degrees in the horizontal, and plus minus. I'm going to get this wrong now. Is it plus minus 20 or plus minus 10? It might be plus minus 20. So it gives a solid angle of about 0.8, I think, 0.8, 0.9 steradian. So it's actually quite large. It's quite a large solid angle. So we're actually getting quite a lot of signal. So this is what you call high throughput spectrometer. Okay. And so we've got all these filter blocks here. So we've got bismuth here, then we've got beryllium, then we've got graphite filter blocks here. They're quite thick too. And then we've got a collimator, and then we've got another beryllium set of blocks here. So what on earth do all these blocks do? All right, so what they do is, I don't know whether you've ever heard of the Bragg cutoff. So a Bragg cutoff is where basically below a Bragg cutoff is where the material becomes totally transparent to the beam, the neutron beam passing through it, right? Above the cutoff, it's scattered away. The neutrons are scattered completely. So one is transparent, the other is scattered. And beryllium is superb at doing this. It has an absolutely humongous Bragg cutoff. And so this is where the cooling comes in at about 300 Kelvin. This is the cutoff here, right? But you can get an order of magnitude increase increase in the Bragg cutoff when you go to 100 Kelvin or below. And we're actually running around 40 Kelvin, okay, for the beryllium, for the graphite, and for the bismuth. Bismuth has a sort of similar cutoff. Now this is in wave numbers. This cutoff here for the beryllium is 5.5 millieV. 5.5 millieV. The Bragg cutoff for the graphite, I keep calling carbon, graphite, and this is what you call nuclear grade graphite. I'm not going to go into that. It's sort of amorphous type graphite, and that is around 1.1 millieV, okay, 1.1 millieV. However, the graphite doesn't do as good a job, and so up here, you're still getting good scatter, but it's not 100% scatter. Okay, it's not basically everything's scattered out. Some of the neutrons will still pass through at higher energies, so that's why we use the beryllium. Now we use the bismuth here because the bismuth has a Bragg cutoff, and the Bragg cutoff is around 5.5 millieV. It's somewhere around there. It's used basically because there is a large resonance in the beryllium itself. So when you pass neutrons through first, if it hits the beryllium, you're going to find a signal in the phonon density of states, and the signal's around 50 millieV, and you don't want that. So to get around that, you first do a sort of a pre-scatter with the bismuth, and then you do all your goodness scatter with the beryllium, and then you've got the graphite, which gives you the final energy of 1.2 millieV. And then you've got a collimator to make sure everything's going in the right direction. All the goodness is going through, all the transmitted things going through. And then you've got a bismuth, I've got another beryllium layer to do a little bit more of tidying up of anything else that's scattered from everything down here, right? That might pass through, that somehow gets scattered back in, okay? And so what you end up is with a final energy of 1.2, so it's cold, 1.2 plus or minus about 0.5. I call it 0.5, 0.55 is what others call it, could be 0.6. We can't measure it really that accurately, so I call it 0.5. It sort of works that way according to when I do an analysis of the full width half maximums. And so that's what you've got there. Okay, so that is your low energy bandpass filter. It's not a line. It's not like an analyzer that you would get, say, a crystal analyzer, which can be sharper. But what's nice about it is it's constant, right? No matter what the incident energy is, we always have the same window. We're always looking at the same window, 1.2 plus or minus 0.5 millieV. Okay, so that's the beauty of it. And because we've got all this bank of detectors, we're getting a large swathe of scatter, which is really nice. And because we sum it up, we're getting a really good estimate of the density of states or the vibrational modes. And so it's a very nice instrument to use, very simple in terms of the actual physics of how it works, and very nice to use. The only thing which is problematic, and which we're still getting our trying to improve. And what spectroscopists, neutron spectroscopists, do a lot of is try to, especially ones that are right on the reactor face, is trying to reduce the background. And so because there's all this scatter going on, we have to really make sure that when it scatters out, right, into the spectrometer itself, or into the actual vacuum chamber, that it doesn't produce more background. So we're progressively adding more and more shielding to that to reduce the backgrounds. Okay, so now how does this actually work? Well, first, you scan the incident energy. And as I said, you scan the incident energy by changing the angle of the monochromator. That's a normal thing. So this whole thing moves around the drum. The whole analyzer moves around the drum, and each time it moves, it's at a different energy. So then we're stepping in energy, right? And we can go from, as I said, around 5 millieV up to about 200 millieV, essentially when we're using when we're using two monochromators. The final energy is constant. Okay. Now, because the final energy is so small, it's only 1.2 millieV. Most of the momentum transfer is due to the instant beam. Okay, so you might as well, the Q, the momentum transfer is mainly due to Ki. You can more or less forget about Kf in this case, but we don't. But you can. Of course, we have because E equals h bar squared K squared on 2m, or Q squared on 2m, and Q is related to the angle. The angle's here. Then we have a swath of, we're looking at a swath of as we change the energy, a swath of Q space, right? So this is Q space here. These are different Brillouin zones in the extended zone. And so the detectors at say at 25 millieV, we have 30 detectors, and they're along here. These 30 detectors see different angles, and these different angles correspond to different positions in Q space. And what we're doing is we're summing up all the intensity within those detectors. Okay. So I think I've explained that enough. I've got to move on. So this is the last couple of slides. You'll be happy to know, and we're sort of nearly there. So this is, as I said, nickel, for example, is a metal, and it produces coherent scatter. It's not as much as say, incoherent scatter from hydrogen, but it doesn't matter. We can still detect it, and we're still sensitive for it because it's in the right energy range. So these are the detectors here, and these are position sensitive detectors. So this is the top of the detectors here, and this is the bottom of the detectors. And 0 means the first detector. That's on the left-hand side. Well, that's on the left-hand side anyway. It's on one side of the detector bank, and then over here is the 29. Is number 29. You can sort of see it here. You can see the actual detectors themselves just by the way they're counting, right? You can sort of see the stripes. This is the 30th detector, and this is the first detector here, okay? And this is at a particular energy. And this particular energy is at 70 millieV, okay? Now we have regions of interest. So this blue curve here is, we've taken a region of interest, and a square, and we've summed all the intensities within this square, and that produces the first point over here, the first blue point, which is 70 millieV. Then there's this strange region here around about 700 bin, the 700 value, to about whatever it is, 950. Okay. Why is that so less in intensity? It's so less in intensity because we stuck a bit of cadmium over the top of the bank of detectors. Now that was originally because we were trying to get rid of some hotspots. Hotspots mean that there are some scatter from other places within the instrument, and they're getting onto the actual detectors themselves. We wanted to get rid of it, but it has the added benefit that in fact we still get intensity, but that's because of high energy neutrons. That's our background basically. So so if we sum this up here, this rectangle up, that produces our background here. right? So for each energy, we get an image like this. We have two regions of interest, one around here, one around here. The blue is here, is this one, and that's the sample. And we say this reduced intensity region is the brown, which is the background. And then we do a background subtract, and lo and behold, we have what we believe is the density of states of phonon density of states of nickel, right? There is a background here, and that is due to just the elastic tail, which we need to subtract off. So I haven't done that, but it doesn't really much matter for this demonstration. This is the phonon dispersion curve. So now we're talking about the phonon curves, phonon dispersion, phonon band structure of nickel, right? And this was taken from, and I forgot to put the, oh dear, I forgot to put the reference down. It's a archives, X-Archives reference 2020 or something, using a particular type of, it's not a DFT calculation, it's another type of calculation, but it's a pretty sophisticated type of calculation as it turns out. So these are dispersion curves. So how do these dispersion curves, so I'm going to tell you, just remind you about a bit of physics again. These dispersion curves can be related to the phonon density of states. Where it's flat, where the curves are flat, is a high density of states. Okay, where the curves is a gradient, it's very little density of states, and so you don't see it. So these peaks here, this corresponds to transverse wave. So you can have a transverse wave, it's going like this, or you can have a longitudinal wave. Okay, so you've got a transverse wave, a longitudinal wave along particular parts of the Brillouin zone. So nickel is facing the cubic. Yes, I think it's facing the cubic. So you have gamma delta X, that's along the 001 direction, for example, or 100 direction, they're all about the same. Gamma sigma X is along the 110 direction. The gamma lambda L is along the 111 direction. Okay. So these points here correspond to these peaks here. And these points here, they get the L point wrong, correspond to this peak here. And actually, it's these what are called critical points really define the phonon band structure. Why do I say that? Is because all these band structures all more or less have the same shape. You can have a look at nickel, you can look at, copper, you can look at chromium, you can look at manganese, in the series, and they're all the same. They all have the same shape. What differs is, in fact, these critical points. And what theoreticians are most interested in are these critical points, because that defines the band structure, that defines the material, that defines the way the material behaves. And so when we do these type of studies, in fact, what we're doing is we don't have to do all the mapping. I mean, it's important to do the mapping in some cases, but in this sort of case for phonon band structure mapping, in fact, the critical points are the most critical, in fact. So with that, I think I've gone to nearly 50 minutes, Kiralee, and I'm going to say thank you so much. Again, I'm so happy that I got the opportunity to speak to you. I hope I did a good job. I'm always feeling I don't do a very good job, but anyway, and I'm happy to take questions. Thank you.